basically, you can calculate by yourself. You convert this 97% to the log scale, and then you can get the 2.3. Yeah, this 2.3 comes from the 97. And if it's just, I think if you just have 50% of the swing, then I think the coefficient is 0.67. So it's just natural log 2, I think, will give you 0.67. And this one you need to do natural log 97, something like that. So this is the delay. And then let's look at the operation. So this is a full timing for this read operation. So what you need to do, as we discussed before you turn on word line, then your bit line needs to be precharged to be half VDD. Okay. So why is half VDD? Any idea?
So that it's symmetric or zero?
Yeah. Because you have 0 or 1, right? So then if you sense, then if you have this bit line to be in the middle, then sensing 0 and sensing 1 will have the same speed. So this is the timing diagram. And now we turn on the word line, and then we have this charge sharing. So the bit line will increase by delta V if we store 1. And after this delta V is developed, we need to turn on the sense amp enable signal. So here this is an array. And for example, this is a cell we want to sense. So we precharge this one to be half VDD, and then turn on the word line. So then we develop this delta V here. And then the sense amp is typically differential. So the other side input for the sense amp will be kept at half VDD. So this side will be half VDD plus delta V. So the sense amp will do something here, so which is important for the DRAM. Because DRAM, if you look at the waveform here, up to this point, the data you store here 1, but actually the voltage is decaying to this point. That means the data is disturbed. And you need to recover this after the read operation because you don't want to change the data. So then this is enabled by the SA enable signal at this moment. So if you enable sense amp at this moment, then we will see later that the bit line and the bit line bar, we'll talk about what is bit line bar later, okay? Assuming there is a reference. Let's look at bit line only, let's say. At this moment, you turn on the sense amp. So then the sense amp will amplify the difference. So the sense amp will make the bit line to be VDD due to this small positive delta V. At the same time, this bit line will charge back the capacitor, and the storage node will also charge to VDD. So you recover the data. Sometimes we call this write back process. So we'll talk about that in a minute, how this happens. So this is due to the sense amp's charge back effect. The sense amp typically here is a latch-based sense amp. So here this is a latch, and this is one inverter, this is another inverter, and they cross couple. So this is like SRAM, the middle part of the SRAM. So it's a latch. And the latch here will have two control. Those two control typically are two, let's say two transistor. Let's say this is PMOS, this is NMOS. So those two control is connected to, for example, VDD and the ground. And those controls, transistor's gate is controlled by the sense amp enable signal. So normally this SA enable is off. So if it's off, this latch is floating. So because you don't have the path to the VDD or ground, so this latch is floating. If the latch is floating and then you precharge the bit line to be half VDD, and your reference, this is reference set, is also half VDD. This is okay for this latch because this is like the meta-stable point, and this is floating, so you don't have the problem here. But once you turn on the sense-sampling enable, after this one becomes half VDD plus delta V. Now you turn on the sense-sampling enable. That means here, this circuit will have the path to the ground and then VDD. So this one will charge to VDD. And this one will discharge to 0 due to the positive feedback because it's a latch. Once the latch has the path to the ground or VDD, then it will flip. But before that, before you turn on the sense-sampling enable, the latch is floating there. Then it's okay. You can have both sides to be half VDD. That's okay. But once the latch is connecting to the ground or VDD, then it must flip. So this is what the sense-sampling enable signal does for you. And then, after you turn on the sense-sampling enable, so this one will flip to VDD. So this VDD, remember, this is bit line. And this bit line is still connected to your cell here. And still, at this moment, word line is on. So that means this VDD is going to charge back this capacitor here. So the capacitor voltage will restore to VDD because here is already decay to this point. But now, since bit line is flipping to the VDD, this bit line is going to charge back the cell capacitor, and the storage node will go back to VDD as well. So after those two go back to VDD, then you can stop the read operation here. So those take time, okay, like a few nanoseconds, plus maybe 10 nanoseconds, and in total, that's why internal DRAM clock frequency cannot increase due to those steps you have to finish. So any questions here? And again, this sense margin, delta V, needs to be carefully designed. And because this delta V needs to be larger than those process variation and noise, because those transistor mismatch and the process variation and the temporal noise, you have to make sure that this delta V is large enough to overcome those variations to have a deterministic output. Otherwise, sometimes you get 1, sometimes you get 0, then that's not good. So we'll talk about the challenges in the delta V design. So you have to maintain the CS ratio, SCS over the CB ratio. Okay, so this is the whole timing diagram for the read operation. This is what we discussed. There are a few steps. Before you turn on the word line, precharge to half VDD, and then after you turn on the word line, the charge sharing will happen. So basically you develop this delta V, and once you have enough delta V, then you can turn on the sense sampling enable, and the sense sample will help you to split the bit line and the reference. So the bit line in this case will be pulled up to VDD, and then at the same time, this bit line is going to charge back the cell storage node. So then both of them will go up to VDD. And after that, you can close the word line, and then after that, you need to pre-charge the bit line to be half VDD again. So this is the process for the read. Any questions?
Is that using the right word line? VPP is higher.
Oh yeah, yes. So this is typical. So in the DRAM design, so the word line gate voltage will reach up to this VPP, which is higher than what you store here VDD. So this boosted word line is just to make the access transistor drive current larger, so you can sense faster. So you boost up the word line voltage for that. Okay, so let's look at the peripheral circuits for the DRAM. And here we have a complete set. And we have discussed about this one, the sense amp. This is sense amplifier. And this is the latch in the middle. And then this is a control transistor as we discussed. This is connected to VDD and this is connected to ground. So this is controlled by this P set and N set, essentially is this sense amp enable signal. So this is connected to VDD and this is connected to ground. And this P set and N set essentially is this sense amp enable signal. And you may wonder how to precharge bit line to be half VDD. Again, this is through this equalizer circuit. You have seen this before in the SRAM case. So 3 transistors like this, and this is the equalizer enable signal. And then the difference is that here you connect to half VDD here by a voltage bias or reference. In the SRAM case, you connect to a VDD, but in this case, you connect to a half VDD bias. So then you can ensure that this node and this node will be half VDD. So this is same as SRAM. The only difference is the voltage bias you provide is half VDD in this case. And then here this is like a pass gate to collect the data from the bit line bar to the outside. So this is outside to the I/O. So you just need 2 pass gate to collect the data from here to outside, or from here to the outside. So you have 2 control, and this is controlled by so-called CSL signal. So this is to fetch the data. Once the bit line is let's say flipped to 1, then you turn on the CSL to sense the data out to the outside buffer. And this is a full cycle, including the write operation. So what we have seen is just the read operation. So this first half is the read operation, the same as before. I will skip that. And here, what you can do is that after the read, you can do the write operation, following the read without closing the word line. So you can still maintain the word line on. So this is word line. And after the data, let's still go through that. Okay. So here you turn on the word line, and then you wait for this charge sharing, and after this delta V, then you enable the sense amp enable signal, and then you will flip the bit line and also charge the storage node back. This is the recover, and then here in this period, because the bit line voltage is stable, you are going to turn on this CSL, and then this data 1 is going to be fetched out. So after that, you just need to wait the cell to be restored to be VDD, and then you can do the write operation. So here, for example, you want to write 0. Then what you need to do is to, and before this CSL and the next CSL, you need to prepare the data 0 ready from the outside buffer. And then that means here you need to change the bit 9 to be 0. If you want to write 0, then the bit 9 needs to be 0. If you want to write 1, then the bit 9 needs to be VDD. So here you need to make the bit 9 to be 0. And then if you make that ready, then you turn on the CSL to allow the 0 to pass from the outside into the bit 9, and then that will discharge the storage node, and then you will have the flip from 1 to 0 here. So after you have done this, then you can close the word line, and after you close the word line, then you need to precharge again to be half VDD for the bit 9. So this is the whole process for the read and write. And here are typical timings. So for different stage, like signal development here, this is delta V. And then sensamp, this is to turn on the sensamp and then sense the data, another few nanoseconds, and you need to restore. That is the read back process. It will take some time. And first the word line rise and falling edge will take some time. And the CSL pulse also takes some time. So if you add those together, then that will be tens of nanoseconds already. So that's why the DRAM clock frequency cannot be like up to gigahertz. If gigahertz, that means 1 nanosecond. You cannot finish all of those in 1 nanosecond. Okay, so then these are some timing parameters. If you look at the spec or the data sheet of the DRAM, it will tell you some of those parameters. So for example, the TRCD is from here to here. This is row to colon delay. That means from the word line to turn on, that means the row input, to the colon output, that means the sense sample is ready. It's already finished the sensing, so this is row to colon. The row is input, let's say input to the row and output from the colon. And then the other important is this TRC. This is total time here. This is called the row cycle time. Row cycle time means this from the word line open to word line close. This total cycle time is like 40 to 50 nanoseconds. And the CSL pulse, this is the pulse to fetch the data out or drive the data in. And this pulse actually is the limiter for the internal clock frequency. And for example, you need 2.5 nanoseconds, okay? And the 2.5 nanoseconds for the interval, then it will be 5 nanoseconds clock cycle, then that will be 200 megahertz. So this limits your internal clock frequency. So I think that's all for today's lecture. So we can continue